Hello, my name is Anurag Dutta and I am an undergraduate at the Computer Science and Engineering Department of Government College of Engineering and Textile Technology, Shrirampur. Today I will be going to present the topic of Plexus Search, which is a search enumeration. So before beginning the presentation of the paper, I would like to thank the organizers of the 2022 USTM-AIMT Summer Conference for hosting this conference and giving us the opportunity for presenting this paper. So now let's begin with the introduction of the paper. So basically the paper talks about some algorithm. Basically it talks about a searching algorithm. So an algorithm is a step-by-step approach of solving a problem. Like if we are given some problem and we will have to just solve them. So we will have to follow some path or some way in which we will be reaching to the solution. So algorithm is like that. So searching is one of the most preliminary yet important algorithm in the world of data structures and algorithms. So it involves searching of elements by their indices from a heap of data. Like if we are having a heap of data, cluster of data, and we want to search for a key amongst them, so we make use of some searching algorithm. Now, we have numerous searching algorithms which are efficient enough. Yeah, they are efficient. But in this paper, we are going to present a new type of searching or a new domain of searching, basically Plexus search, which is sufficient enough to search in, I mean, all the dimensions. Like they can work well for one dimensional data set, two dimensional data set, three dimensional, and more higher dimensional data set. But the best shine of our algorithm could be seen if we are about to like implement our algorithm on any higher data set. So higher dimensional data set. So yeah, it is great for that. So in the next slide onwards, we will be discussing about the algorithm that we are going to propose. So firstly, let us have a set of n numbers and that is represented as alpha 1, alpha 2 and it goes on up to alpha n. And these elements are arranged in such a order that alpha I will be less than or equal to alpha j for all j greater than I. Now we could imagine these data elements in the form of a 2D square array of order square root of n enclosed under a ceiling function. So as we know that the value of n will be somewhere less than or equal to the product of square root of n, ceiling of square root of n plus ceiling of square root of n for all n becoming some element of the integer. So basically we are left with two possibilities that n equals square root of n cross square root of n and n being less than square root of n cross square root of n. So from the next slide onwards we will be discussing about them in detail. So firstly, if we are having n equals square root of n cross square root of n, then the 2D square array that we want to search from, like this 2D square array is the one from which we want to search for the key. So that can be thought of like this. So yeah, this is the representation which I mentioned. More formally in terms of indices, we can write it as like 0001 and it goes to like this. So yeah, this is a formal representation of the square that I talked about in the previous slide. Now, if the value of n is somewhere less than the product of both of them, then it's very obvious that the square array that we are talking about isn't filled completely. So the remaining portions or the remaining indices that are not filled will be filled as alpha n plus 1, alpha n plus 2, alpha n plus 3. It will just go on like that until and unless the square is completely filled, right? So now coming to the searching part. So firstly, we will be searching along the diagonals. Now we know that some rectangular figure, like we can consider a square as a rectangle also, and so the matrix, that is the square matrix, will in some way be equal, will be some way similar to that of the rectangle. So we know that in a rectangle there are two diagonals, So like we will be searching along the diagonals at once. So if we are having a n cross n matrix, so we know that the number of elements that are present in the diagonals can be easily counted. Similarly, for a n cross m matrix, it can also be counted. So firstly, we will be running a search along the diagonals, which is bound to take some constant time, since we are bound to know that the value of the diagonals is constant. Like, so we will be doing that, and the probability for finding that value of k along the diagonals is like 2 upon square root of n minus 1 upon square root of n plus square root of n, if the value of square root of s in the square root of n is some odd number. But if at all it is an even number, the probability of finding that will be 2 upon square root of n. Now, if we are finding that element in some of the diagonals, then we will be stopping the search, and yeah, we have found that number. So that's great. Now, if it is not found, then we will be dividing that square array into like 4 sectors. So the 4 sectors could be triangular ones or trapezoidal ones, depending upon the value of square root of n. Like if it is a odd number, then we will be dividing it into triangular sectors. But if it is a trapezoid, if it is an even number, then we will be dividing into trapezoidal sectors. Now the dimensionalities of the 2D sectors could be defined accordingly, like their base, height, and all that. So next, we will be looking into the maximum and the minimum that each of the sectors can have. Like I have mentioned those maximum and minimum that they could reach in the next slide, like the positions where their maximum and minimum is supposed to be found. So we will run, check amongst each of these maximum and minimum, and we will find the range in which the key which we are searching is about to fit. Like the range, if it is found, then we will be running a search in that range, and we will get the value. I mean, we are supposed to get that value if at all it is present in the array. So yeah, this is the chart for the maximum and minimum which is supposed to be there, and these are the indices where the maximum and minimum in the sector 1 is supposed to be found. It is when like it is an odd number and when it is an even number. Now let us move to the efficacy of the algorithm. In the best case, our algorithm will be efficient enough to solve in constant time, and in the average and worst case, it is supposed to take linearithm time, which is quite great if we see in terms of the general 2D linear search which exists, like the naive approach. So, this is the comparative analysis with the pre-existing naive approach that we used to do for higher dimensional data structures, like for example 2D data structure. So let us come to the conclusion of the topic. So Plexus is a non-heuristic searching technique that can work well for data structures in the dimension of 2 as well as in the dimension of 1. It is quite fast in comparison to the trivial 2D linear search which operates at a quadratic time complexity. It has an optimal searching efficacy of linearithm time. So yeah, it is quite good. Uh, so the next slide is about the references which I took help from for preparing this paper. So, so yeah, thank you for giving us the opportunity again. Hope you have a nice day. Bye.